Greg is a second-year student working on verifying systems with ML components. And this is another distinguished PLEI paper this year.
All right. Hello, everybody. Thank you for coming. This is joint work with Shankar Pailor, Ishal Dillig, and Swaraj Chaudhary. So in recent years, neural networks have increasingly come to be used in safety and security critical settings. So things like autonomous cars or drones, other kinds of cyber physical systems, or in security settings like malware detection. And in these kinds of settings, we want to know that the network is going to behave in some reasonable way. But the problem with that is that it's been known for a number of years now that neural networks are subject to what are called adversarial examples. And the idea with adversarial examples is this. I start with some input, say, for example, this panda on the left, where my network is well behaved. You know, my network says this is a panda, I say this is a panda, everybody's happy. But the problem is that I can now exploit the structure of the network and modify this input in some very slight way and cause the network to misbehave. So even though, you know, this image on the right, it looks the same to us, but the network now classifies this as a gibbon. And so this is a problem. And, you know, it can seem a little silly to, you know, when we're talking about pandas and gibbons and, you know, who cares whether the network can recognize a panda. But it's been shown that you can actually cause the same kind of problems in the real world just by placing a small sticker on a stop sign. And obviously that can have some major safety implications. So what we would like to do is show that the network is free of these adversarial examples. And this is precisely what the property of local robustness, or robustness for short, says. Essentially, the idea here is if I start from some input and I make some small perturbation to that input, I can't change the output of the network. And so, for example, if I have some stop sign, the small perturbation might cover things like putting a sticker on it. And we would say, you know, if the network can recognize this stop sign to begin with, and we put a sticker on it, the network can still recognize this stop sign. But in order to describe our work, I'm going to need to be a little bit more formal about robustness. So let me just briefly introduce it in a little bit more detail. So let's suppose we have some network and some input to the network, which is classified into this class K. And I want to make one note here. For the rest of the talk, when I talk about the input to a network, what I really mean is some vector of real values. So we're assuming that whatever featurization you want to do has already been done at this point. So the first thing we need to do is characterize this notion of a small perturbation. And in general, what we can do is just define some set of points in the input space to the network. So for example, this region I corresponds to some epsilon ball around x0. But you can have many different regions that you're not limited to this form. And then, given this region, a robustness specification just says that every input in this region is classified into this class K. And the only slightly strange thing here, I think, is this argmax. And that comes from the fact that when we run a network, what we actually get is some score for each possible output class. So really what I'm saying here is that when you run the network N on some input X, K is given the highest score among all the possible outputs. So of course, we're not the first people to try to explore this area or to try to prove that networks are robust. So let me briefly review a little bit of existing work to put this into context. So in general, existing approaches for verifying network robustness have sort of fallen into one of two camps. Some techniques are sound but incomplete. So for example, this is AI squared. And these techniques are generally quite fast. They can scale to reasonably large networks, and they can be quite efficient. But they won't always be able to find a proof, even if the network you're looking at is really robust. On the other hand, there are some techniques that are both sound and complete. For example, ReluPlex is in this category. And in principle, these techniques can always find a proof for any robust network. But these techniques tend to be quite slow. So with that in mind, the goal of our work is to develop a new technique for analyzing neural network robustness that is sound and complete, but also efficient enough to scale to reasonably sized networks. And in particular, what we'd like to do is take a network and a robustness specification and provide either a proof of correctness or a counterexample, some witness to the violation of the robustness property. And we're going to do this by combining some kind of proof search and some kind of counterexample search in a synergistic way. So let me briefly describe the proof search and the counterexample search. So proof search is based on abstract interpretation. And the idea here is pretty simple. We start with a network, and this thing looks quite complicated and a little bit scary. But if you look at it sort of purely operationally, and you just think, what numeric program is actually equivalent to this network, it's very simple. We just have some straight line program. There's no loops or conditionals. And so we can use standard abstract interpretation techniques to analyze this program. And then we can just check some relatively simple assertion. And if we satisfy this assertion, then our network is in fact robust. Our counterexample search is based on numerical optimization. So the idea here is if we start with a network and some robustness property, we're just going to optimize some objective function. And what exactly this function says is not super important for this talk. But the idea here is that if the value of the objective function at some point is low enough, then that point is really a counterexample to the robustness property. And the other thing I want to note about this function is that it's continuous, and in fact it's almost everywhere differentiable, which means that we can use normal gradient descent techniques to try to find this optimum. And in particular, there's a well-known technique called projected gradient descent, which we can use to do this optimization subject to this constraint that x has to be in the input region we care about. However, as with most gradient descent techniques, this may fail to find a counterexample because the optimization is not guaranteed to converge to some global optimum. So that brings us to the key question of our work, which is we have a proof search and we have a way to search for counterexamples, but how can we combine these two things in some smart way to get something that is sound, complete, and efficient? And so clearly, if the proof search just works all with no sort of intervention, or if the counterexample search works, then we're done. So really the interesting case here is what happens if we can't find a proof or a counterexample? And there's two things we can do. First, we can make sure we're choosing a good abstract domain. And in general, this will help our proof search because a more precise abstract domain can help us to analyze more precisely. So if we start with some input region I, let's say, and we transform this under some not very precise domain, something like intervals, for example, we may include some bad point, some point that violates our assertion. But if we take the same input and we transform it under some more precise domain, like polyhedra, maybe we can exclude this bad point. So we can, by choosing a good abstract domain, we can improve our proof search. The other thing we can do is we can refine the input region. And when I say refine, what I really mean is we're going to partition the input region into two pieces, and we're just going to consider each piece separately. And this improves both the proof search and the counterexample search intuitively because each piece is now just searching over a smaller space, and so they can both be more precise. So for the proof search, for example, we do some abstract interpretation, we get some bad point, and now let's say we refine. In the next iteration, maybe we do some abstract interpretation, but now we have these two separate pieces, and we can maybe exclude this bad point that we had before. And similarly, for the counterexample search, we recall that our optimization gives us back some point, but it's not guaranteed to be some real counterexample. So if this is not a real counterexample, let's say we bisect the input region, and now the gradient descent procedure is working in these two smaller spaces separately so it can be more precise. And in particular, in the left half of this space, you can just remove that spurious counterexample entirely. So now that I've given you some background on the proof search and the counterexample search and how we're going to combine these things, I want to come to the overview of our technique. And in order to help illustrate this, I'm going to put a robustness property on the right side and sort of step through that with this property as an example. So to start with, we take some neural network, some abstract domain to use initially, although we'll change abstract domains later, and some robustness property that we want to verify. And we'll start by searching for a counterexample. And so you can see in the right side, we come up with some point in our space. And then we'll check and we'll see if this is a real counterexample. And if it is, then of course we're done. But let's say in this case, this is not a real counterexample. This point actually does map to the output class that we want. Then we move on to our proof search. And so then we're going to use the domain that we start with, and we're going to try to prove that this region is in fact robust. If we're not able to prove, or if we are able to prove that, then of course, again, we're done. We've proved the property. Otherwise, we're going to go into this refine block, and what we're going to do here is the two kinds of refinement that I mentioned earlier. So we're going to both partition the initial region into two pieces, and we're also going to select an abstract domain to use for each piece. And then we will restart this search. So on the right here, I've shown one way that we might partition the region. Now, I think it should be clear from this picture that this refine block has a big impact on the efficiency of our tool. In particular, choosing the right abstract domain and choosing a good partition for the input region is going to make a big difference in terms of how fast we're able to verify any property. So I want to talk a little bit about how this refine block really works. This is controlled by something we call a verification policy. So let me talk about that. At a high level, the verification policy does exactly what I described. It takes some network and some robustness property, along with the results from the previous round of analysis. So that's the results of the proof search and the counterexample search. And it's going to produce some partition of the input region, along with some abstract domains to use in the next round. But there's a problem here, which is that we're analyzing neural networks. And neural networks in general are quite opaque. They're not very intuitive, and they're hard to interpret. And because of that, it's unclear how we should really write this verification policy. It's unclear what kind of policies will give us good results. But lucky for us, we're doing machine learning. And so, as is usual in machine learning, when something is hard, we can just make the computer do it. So that's what we're going to do here. We're going to learn a verification policy. So if you recall the overview of our technique, we're now going to add a new offline training phase. So before we try to verify any properties, we're going to choose some training problems, and we're going to learn a verification policy from them. And I don't have a lot of time now to get into how this training is actually done. We use a well-known technique called Bayesian optimization, and I'd invite you to read the paper for more details. So with that, let me conclude the technical part of the talk and move on to the evaluation. We implemented our approach in a tool we call Karen, and we evaluate Karen on approximately 600 benchmarks in an effort to find answers to the following two questions. First, we want to know, is Karen more efficient than existing complete approaches for analyzing neural network robustness? And second, we want to know, is Karen more precise than existing incomplete approaches? So to compare against complete approaches, we compare with ReLU-Val and ReLU-Plex, two existing complete approaches. And what we find is that if we look at how many benchmarks each tool can solve within some fixed timeout, Karen is able to solve 2.5 times more than ReLU-Val and more than 16 times more than ReLU-Plex. So this suggests that, in fact, our approach is able to scale much better than existing complete tools. For incomplete tools, we compare against AI squared. And AI squared is based on abstract interpretation, and it's parametric over the abstract domain. So in particular, we instantiate AI squared with two domains, which I've called AI squared fast and AI squared precise on this slide. The fast domain is just some faster but less precise domain. The precise domain is more precise and slower. And both of these domains were chosen from the AI squared paper. And the takeaway here is that Karen is able to solve 60% more benchmarks than AI squared precise and 85% more than AI squared fast. And this is, again, in the same timeout. What's really notable, I think, also, is that not only are we able to be more precise than incomplete approaches, but we're actually able to be just as fast or faster than existing incomplete approaches. So here what I'm showing you is for a subset of the benchmarks. On the x-axis, the number of benchmarks that were solved, and on the y-axis, time. So the idea here is that being further to the right and down is better. And what we can see is that Karen is actually, on average, 6 times faster than AI squared with its more precise domain, because Karen is able to choose better domains and then refine rather than having to use this slow domain from the beginning. And in addition, Karen is even comparable in speed to AI squared using the fast domain. So I think what I've described here is a good start, but there's some future work that I think is really interesting to explore, and I want to highlight 2 directions in particular. The first is to introduce different kinds of proof search. So what I've described, our proof search, is based on abstract interpretation, but in general, people have come up with many different ways to try to search for proofs of robustness. For example, based on solvers or mixing solvers with abstract interpretation. And when I was referring to choosing a domain, there's no reason we really couldn't choose a domain or choose a solver or choose some other approach rather than just picking some domain. The other thing I think would be interesting to look into is different policy learning techniques. So we've used Bayesian optimization for this work, but obviously Bayesian optimization is not the only way to do machine learning. And I think it'd be interesting to see what happens if we try some different ways to learn this verification policy. So in conclusion, we have developed a new technique for verifying neural network robustness, and this technique is able to scale more efficiently than existing complete approaches while also being able to be much more precise than existing incomplete approaches. And with that, I'm happy to take questions. Yeah, we're working on it, but we haven't open sourced it yet. But we're working on it.
Okay. Another question is, since the verification policy is actually learned,
yeah. Okay. Well.
Okay. Since the verification policy is learned by training another model, actually, so it is possible to reinforce the refinement process will never terminate, right? So how do you guarantee your operation actually complete?
Oh, so the question was the verification policy is learned from some data, and so is it guaranteed that the policy will be able to terminate? And the answer is yes, because the space of policies that the model is choosing from is restricted. Basically, there's a lot of details about this in the paper, but this partitioning is guaranteed not to put the entire region into one piece. So you will always make the region smaller each time you partition, and so eventually you can always terminate.
The concern is usually deep neural nets capture a very weird nonlinear, certain high-dimensional region. Maybe actually it's a word manifold. So if you use polyagent domain, it's possible you will never be able to exactly capture that particular shape.
I'm afraid I don't quite understand. Okay.
So I'm just wondering what kind of activating function you can deal with. Is this only values, or can you also handle sigmoid?
Oh, so currently it only oh, sorry. The question is what kind of activation functions can we handle? Currently we can only handle ReLUs, but since our proof search right now is based on abstract interpretation, if you define abstract transformers for other activation functions, we could handle those as well.
I see, but if you're doing things like counterexample search, a nice thing about random-based network is that it's basically a piecewise linear function. And you happen to split the region in a way such that one region is just a linear region. It's very easy to find the counterexample. So do you see, so will it be a problem for things like sigmoid or tan?
Okay, so the question is if we extend this to handle other activation functions, things that aren't piecewise linear, does this splitting make the counterexample search harder? Is that what you're asking? Yeah, so it does not, because the counterexample search is just using some projected gradient descent, so you can basically do the same thing, because all you're doing is gradient descent and then projecting back to a space.
The second question I have is that I noticed some of the baselines maybe not the most up-to-date. I could look at more recent papers. One example is that Martin Munch's group had a paper at Polo this year. It's called Deep Poly. And also Ross Patrick from MIT. They have a complete solver for robustness at IPA this year.
Okay, so the question was about some recent work that's come out since we submitted the paper. So,
I think that was before your submission.
oh, Papa was before, yes, sorry. Some of the other work came out after, but so deep poly is just a different abstract domain. So it's easy, basically, it's easy to add that into the system as another domain that you can choose. And then other works, things like Neurify and Refine Zono, I'm interested in those because I think we can take some techniques and incorporate them into our tool, but I haven't done that yet.
Do we have time for another question?
I think we have time for one more question.
Okay. Nice talk.
Thank you.
Nice work too. So I had a question about if you have an idea how you might generalize your technique to more general safety properties, because local robustness is a property that many of us are analyzing because lends itself to some formal reasoning, but if you translate it to the real world, we don't really know who's going to give us this epsilon, right?
Yeah.
Who's going to give us the size of that white patch on the stop sign. So do you know how you might generalize to either more general notions of robustness or general safety properties?
So yeah, the question is about generalizing to other kinds of properties besides local robustness. I would say that at least for now, it's very unclear what other kinds of properties we should care about. I don't know if you have any specific properties in mind.
Perhaps the kinds that Reluplex was able to express and handle.
So Reluplex properties, the Reluplex's properties are sort of custom tailored to their domain, correct? So I haven't looked into it. I think it should be possible because what we're doing basically is some abstraction refinement with some fancy learning on top. So I think it should be possible.
Thanks.
All right, this concludes the session. Let's thank all speakers once again. Have a great PLDI.